In this video, we present a new approach to planning hopping trajectories over discontinuous terrain. Legged robots have an advantage over other types of robots because they can traverse cluttered environments with uneven terrain. However, a number of factors make it difficult to plan optimal motions in these environments. For example, it's challenging to plan footsteps when the terrain is discontinuous. Also, the planner must navigate around obstacles. These challenges are further complicated for dynamic movements because the planner must consider friction constraints, actuator limits, and the robot's dynamics. We proposed a new method for planning dynamic hopping in cluttered terrain based on a mixed integer program formulation that simplifies the dynamics by considering each stance phase as impulsive. This change allows us to address many other constraints related to 3D orientation dynamics, contact choice, and obstacle avoidance without introducing a significant computational slowdown. Compared to previous MIP locomotion planners, this approach of simplifying the contact dynamics provides a more coarse motion sketch. However, we show that a motion polishing optimization step with contacts fixed restores dynamic feasibility while also biasing the optimization towards a favorable local optima. We compared our impulsive stance MIP formulation against an equivalent MIP with a full stance phase. For each formulation, we solved 100 path planning problems in randomly generated environments, limiting the max solve time to 60 seconds. The solver found feasible solutions to all of the problems in the impulsive stance formulation within roughly 5 seconds, but it found feasible solutions to only 13 of the problems in the full stance formulation within the 60-second time limit. It did not find a feasible solution to any of the full stance problems with the cost function. The results show that our proposed method decreased the average solve time by at least an order of magnitude, even when accounting for the motion polishing step. We now present videos from our hardware experiments with the MIT Mini Cheetah. We initially tested our approach on simple forward jumps on and off level boxes. We then validated our approach on incline boxes and in an environment that required multiple jumps. We now showcase the decision-making ability of our MIP. The task is to get to the other side of the boxes. In the top experiment, the MIP chooses a path on the angled platform because it is lower to the ground and requires less control effort. However, after we moved the angled platform outward about 10 centimeters, the MIP chose to jump on the taller box instead. In future work, we'd like to extend the impulsive stance formulation to allow for more gaits such as bounding and trotting. We're also interested in improving the constraint handling of MPC to eliminate foot shattering.